Hello and welcome back to this tutorial on credit card fraud detection using multiple anomaly detection methods programmed in Python through Jupyter Notebooks. So in the last video we successfully built and set up our data set, which included 284,000 data points, but we went ahead and downsampled that a little bit so we would have a more reasonable data set to work with. And that fraction I did was about 10%. So we have 28,000 credit card transactions, a total of 49 anomaly cases, and 28,432 valid credit card transactions. And we went ahead and separated that into an X, which is the data with all of the columns that we are interested in, and then a Y, which is the target column or class, 0 being valid transaction and a 1 being a fraudulent credit card transaction. So now we are in a position to go ahead and move on to actually fitting this data and trying to predict which ones are outliers. So as per usual, we need to import the packages that we are going to be using, and these are going to come from sklearn. So the first ones are metrics that we are going to use to determine how successful we are in our outlier detection. So we'll do an accuracy score and a classification report. And I made a spelling error here, so let me go ahead and correct that. And then from an ensemble method, we are going to import the isolation forest. And we'll talk about what and how these methods work in a sec. We're also going to use the local outlier factor. So these are two common anomaly detection methods from the sklearn package, and these are commonly used. You might also see things like a support vector machine used for outlier detection. That takes a little bit longer to train in this case, so with 28,000 data points, actually computing the support vectors to build a machine like that would take a while. So this is why I'm only doing the isolation forest and the local outlier factor. Okay, so let's talk about these methods for a sec before we get started. The local outlier factor is an unsupervised outlier detection method, and this goes ahead and it calculates the anomaly score of each sample, and we call it the local outlier factor. So it measures the local deviation of density of a given sample with respect to its neighbors. It is local in that anomaly score depends on how isolated the object is with respect to the surrounding neighborhood. So we're talking about neighbors here, and this is going to be determined in the same way as the k-nearest neighbors method. So we are actually doing something very similar. However, we're calculating an anomaly score based off those neighbors. The isolation forest algorithm is a little bit different. It's going to return the anomaly score of each sample using this isolation forest method. So it does that, and it isolates the observations by randomly selecting a feature and then randomly selecting a split value between the maximum and minimum values of the selected feature. So we're going to have all of the different columns here could be considered a feature. Since recursive partitioning can be represented by a tree structure, the number of splittings required to isolate a sample is equivalent to the path length from the root node to the terminating node. So if you're like me, that doesn't make a lot of sense to you. However, it's more easily understood if we go into what exactly that means. So this path length averaged over a forest of such these random trees is a measure of normality and our decision function. So random partitioning produces noticeably shorter paths for anomalies. Hence, when a forest of random trees collectively produce shorter path lengths for a particular sample, they are highly likely to be anomalies. So this is a combination of the random forest algorithms, and it's doing that to isolate points which have these shorter path lengths or are more likely to be anomalies. So if you want to read more about these methods, I encourage you to do so. However, for now, we'll go ahead and just dive into programming them up in Python and then seeing what type of results they produce. in machine learning, it's really important that you understand the algorithms that you are using, because you need to pick the algorithm that is going to be the most successful. A lot of the times it's a good idea to compare multiple methods. For example, we're comparing these two in this tutorial. However, even narrowing it down to 2 different machine learning methods is going to require a lot of foresight. So it's just something to consider. So to start, I'm going to define a random state so that we're all on the same page here. And then I'm going to define the outlier detection methods. So this is where we're actually going to import these different algorithms. So I'm going to put this into a dictionary of classifiers. So what I'm going to have is I'm going to have the first one, an isolation forest. And this is simply type isolation forest with no space. And then we have to define a couple parameters. So the first one we're going to have is the max samples, and we're just going to put this as the length of x. So the max samples is the total number of samples that we have. It's going to have a contamination, which is the number of outliers we think there are, and we know this, it's actually the outlier fraction that we calculated earlier when we were going through our data set. So we went ahead and we calculated that up here, simply the number of fraudulent cases over the number of valid credit card transactions here. Okay, we need one more, and that is going to be the random state that we defined above. So we'll just say equals state. All right, so that's the first one, but we also have the local outlier factor. So local outlier factor. And this has a couple parameters as well. So the number of neighbors to consider, this is what goes into the k nearest neighbors method that it uses. We're just going to set this as 2020 as kind of a default or a standard. The higher the percentage of outliers in your data set, the higher you're going to want to make this number. So I might even try to play around with this a little bit and lower this down and see if it produces different results. And once again, we need the contamination. And this is, once again, equal to our outlier fraction. Let me get some spaces. There we go. So that's our dictionary of our different classifiers. Let's go ahead and do a shift enter here to make sure that everything imports correctly and that we're defining these methods correctly as well. And it looks like we are. So yes, it successfully went ahead and got that. So we are good to go to move on. So let's actually fit the model. So this is where the fun begins. But first we are going to have to define a variable called the number of outliers, and this is going to be equal to the length of fraud. This will be referenced a couple times, so we're just going to go ahead and define this ahead of time. And what we're going to do is we're going to do a for loop through the 2 different classifiers that we defined above. So we can say for I, and what we're going to do here is we're going to enumerate our list of classifiers so that we can cycle through them. And this is a dictionary, so we can index it in this way with the dot items. And you know it's a dictionary because we use these brackets here. Okay, so we need a colon here to round out our for loop, and so we can go ahead and start defining things now. So we're going to have to do 2 different steps here, actually, because it's a little bit different if we're using the local outlier factor versus our isolation forest. So what I'm going to do is I'm going to do if CLF name is local outlier factor, then I'm going to do the following. that is going to be we're going to do a y prediction here. And so for the local outlier factor, you can do this convenient function, which is called the fit predict off of x. So it is going to fit the x data, which was all of our columns without the class, and then it's also going to predict the labels for those values. So let's get the scores here. Scores predictions. This is going to be CLF negative outlier factor. So that'll come in handy later. And so we'll move on here. So if it's not the local outlier factor, in other words, it's our isolation forest, we are going to do CLF.fit off of x. So we have just the .fit function here. And then we're going to do scores predicted is going to be the CLF.decision function that it generates off of x. And then finally, y predict is going to be the CLF.predict x. Okay. So that should give us everything that we need. It's doing two different fitting methods depending on whether or not it's the local outlier factor. It's going to do a fit predict, and then it's just doing a normal fit and a later predict if we're using our isolation forest. Okay, so there is one thing we have to do though before we can move on. The results, these y prediction values that we're going to get back, are going to give us a -1 for an outlier and a 1 for an inlier. So that is useful information, but we need to process it a little bit before we can compare it to our class labels. Because if you remember, our class labels are either 0 for valid and 1 for fraudulent. So that's why we have to change this a little bit. So we want 0 for valid, 1 for fraud. So we can do that by simply pulling up our y predictions and then indexing them based off the y prediction is equal to 1. And then what we can do is we can reassign this to 0. So this is taking all of our inliers and classifying them as 0 or a valid credit card transaction. We're also going to do y predict indexed by our y predict equals -1. So our outliers here, the ones that we think don't belong with the rest of the transactions, we are going to classify these as our fraudulent transactions. Okay, so that should be good to go there. What we want to do now is we want to calculate the number of hours, or the number of errors. So what we need to do is a comparison to y. If you remember, y is our target. So y is the values of fraudulent or value or valid 0 or 1 for each individual case. So what we can do is we can do the number of errors here, and this is going to be equal to our y prediction when it does not equal y. And what we're going to do is we're going to go ahead and sum these. So that'll give us a total number of errors. Finally, what we want to do here is we want to run the classification metrics, because this is going to tell us much more useful information. So what we want to print out here is going to be this first part. So we want to give us a name and the number of errors here. So to do that, we're going to do a .format, and we'll have a CLF, name, and the number of errors. Okay, so that should print out the name for us. Alright, and then we want the accuracy score here. So this is one of the metrics that we imported above. Score, and we're going to do a y, the values that we want, and our y predictions, what we think they are. Alright, and then we're also going to print out a classification report. And we'll see very quickly why this classification report is going to be important. So once again, comparing y to what we predict our y. So it looks like everything is good to go. We initialized our classifiers up above, but let's go ahead and do a shift enter here and see if this is indeed going to work. So we're thinking, and here comes our first one. So we have a local outlier factor here, and we had 97 total errors, so relatively high. But if you see, we were 99.659% accurate, so very accurate. But you'll see if you look down here at our precision recall and F1 score, you'll see that we're not quite as good as we think. So what this is saying is, for class 0, we had a precision of 100%, but for class 1, we only had 0.02. So that actually is not very good. So that means that we have very few actual fraudulent cases that are getting labeled as fraudulent cases. I think we only got about one of them correct here. So precision counts for false positives, which we were assigning a bunch of the valid credit card transactions as positive as well. And the recall accounts for false negatives, and so not good with false positives or false negatives at all. And the F1 score is a combination of those. However, our isolation forest was a little bit better. So we had 99.75% accuracy, but we had a precision of 30%. So that's a lot better than 0.2. But still, we're only correctly identifying about 30% of our actual fraudulent cases. So we do have a lot of false positives as well. So we're going to be frustrating our customers because we're always calling them asking, did you make this transaction? But we have the recall of 1 percentage point better, so not good as well. So we had a couple of false negatives. We should have classified a few as fraudulent when we did no such thing. However, our F1 score, better for the isolation forest than the local outlier factor. So since this data set was sufficiently complex, our random forest method or random forest based method was able to produce better results. So 30% of the time we are going to detect the fraudulent transaction. So as long as the criminals in our case make 4 transactions, statistically we will find them every time. So there are better methods out there than this. Since we do have labels, you can use things such as neural networks. However, this is an interesting data set to explore with anomaly detection. Again, we could probably improve our results if we went back and we took a larger sample of our data. We have 284,000 cases here. However, that is going to be computationally expensive. As it is, it already took probably 20 seconds to do the isolation forest method here. So if you can imagine increasing that semi-exponentially, you're going to really increase the computational requirements of this program. So that is why I cut it down. Well, thank you for following along. I hope that you were able to learn a lot of new information. In this tutorial, we went over importing a CSV data set, pre-processing that data set, as well as exploring the data and describing the data so that we knew what we were working with and we knew what information we had. We did histograms to see if there was any unusual parameters. We went ahead and we separated into fraudulent and valid, determining the outlier fraction, which was very low, less than 1% here, 0.17% actually. We did a correlation matrix to show which parameters were important for our class, and we saw some variations here, so we knew that we'd be able to make decent predictions. We separated these based off of our target parameter, which was the class. And then we used 2 different methods, the isolation forest and the local outlier factor, to do anomaly detection on this data set. And this was also a valuable lesson in the importance of understanding your data and understanding precision and recall, but because we showed that we had a 99.65% accuracy, but we were only accurate because there are so many more valid cases than fraudulent cases. So we were very bad at actually detecting the fraudulent cases with our local outlier factor. However, with the isolation forest, we achieved almost 30% in detection of those outliers or those fraudulent cases, which still isn't great, but it is a significant step in the right direction. Once again, thank you for following along. I hope you enjoy the future projects. Thank you very much.